Hey everybody, welcome to the final lecture for Chapter 13, Ethers and Epoxides, Thiols, and Sulfides. This lesson will be covering really the last part of it, which is on the thiols and sulfides. Thiols are any organic molecule that have an SH group, which we could call them a mercapto group. Also, the SH group is akin to an OH group, a hydroxy group, because oxygen and sulfur are in the same group of the periodic table. Some naturally occurring thiols here. We have cysteine, which is one of the 21 known amino acids that make up proteins. Cysteine is just a dimerized form of cysteine. You'll learn more about this today in this lecture, but also more specifically in biochemistry or in a biology class where you're learning about proteins specifically. Biotin is a vitamin B7. Glutathione is a naturally occurring antioxidant. Methionine is an amino acid, one of the essential amino acids. Penicillin is an antibiotic as well as sulfanilamide. And then thiamine chloride is vitamin B1. Here are some other exemplar thiols. Methane thiol here comes from oysters and some cheeses. This looks like Etta cheese there. We've got onions that can give us 1 propane thiol. We've got 2 propene, 1 thiol, which comes from garlic. So now you could associate onions and garlics and oysters and maybe rotting cheeses with bad smells. But they don't have to be bad smelling. So, I mean, I personally like onions. I personally like garlic. If you do it right, things like garlic butter, those are great. And that smell, the odor you get from them, that characteristic smell of those is from these sulfur-containing compounds. Now, other bad ones, I would say, would be from the skunk. You have trans-2-butene-1-thiol, 3-methyl-1-butane-thiol. Those are clearly awful-smelling chemicals that skunks release when they're trying to get away from predators and such. The chemicals at the bottom are not thiols, so I don't need to mention them really, but they do come from the flowers there. Apparently, I guess skunks are attracted to the smell of geraniol, 3,7-dimethyl-2,6-octadiene-1-ol, and then the 2-phenylethanol, again, coming from those roses or geraniums. All right, naming thiols. We're going to name them similar to the rules for alcohols, but it's like just, all the rules of substituents and all of that, parent chains, those are going to be the same. As far as the suffix of the thiols, you're going to keep the E suffix of the parent chain. So, for example, we have in the left chemical, we have carbons 1, 2, 3, and 4. So that's a butane derivative, right? Ane because there's no double bonds. Bute because there's 4 carbons, right? There's a methyl group at carbon 3, so 3-methyl. The alcohol here, the hydroxy group, is at carbon 1, so it's 1-butanol. But for the thiol, we would number it the same way, 1, 2, 3, and 4. We have a 3-methyl group, and the SH, or the mercapto group, is at carbon 1. Notice here we have NOL, but for these it's butane. We keep the E in, and then you affix thiol to the end of the parent chain's name as a suffix. So it's 1-butane thiol there as one whole word, essentially. And so the molecule is 3-methyl-1-butane thiol. If the thiol is a substituent group, it's called mercapto. So in the molecule on the left, we have an alcohol, we have a thiol. The alcohol is a higher priority functional group, so you see it's going to end in this 1-butanol because of the alcohol. There's a methyl group at carbon 3. There's a thio group or a mercapto group at carbon 3 as well. Then you're going to do it alphabetically. So 3-mercapto comes slightly before the 3-methyl alphabetically. I mean, there's only 2 options there, but they're pretty close alphabetically if there were other ones, but the mercapto comes first. If you have multiple thiol groups, right in the molecule on the right, you see this is called dimercaprol. That would be a common name for it. It would be numbered from left to right, 1, 2, and 3. We have the mercapto groups at carbons 2 and 3, 2 and 3 there. So it's 2, 3 dimercapto, and then 1 propanol. All right, now preparing thiols. We have this alkyl bromide with sodium hydrosulfide, and that'll make this thiol right there. That would be 1-butane thiol. And then sodium bromide. The hydrosulfide is a good nucleophile because the sulfur is going to have a negative charge on it, all right, and the bromine is a really good leaving group. Sulfur is a pretty big atom, but bromine is much bigger. So when you're comparing the anions that are possible, we have this being much more stable in solution than this. And going back to pKa values, you would be comparing the pKa of hydrosulfuric acid, H2S, versus hydrobromic acid, HBr. The pKa of H2S is around 7, and the pKa for HBr is negative 8.7, or about there. So you can see that the HBr is many times more acidic than H2S. H2S is a weak acid. It is acidic, but it's the HS minus ion is going to be less stable in solution than the Br minus. So it'll dominate by having this go to the right. Keep in mind this is undergoing an SN2 reaction because you have a primary carbon right there. So that S minus can easily attack and kick off through SN2. One of the earlier examples of thiols in nature was the cysteine, which is actually a class of a disulfide. I mentioned that it was essentially a dimer of cysteine amino acids. Here we have this disulfide being ethane thiol. You don't need to number it 1 and 2 because if the sulfur was over here and this one didn't exist, then it would be numbered 1 and 2 like that. So it's just ethane thiol, and it can react with itself in a basic solution with bromine there to make this disulfide. Again, an example of the disulfide in nature would be the cysteine, which is, again, the cysteine amino acids being oxidized to the cysteine. Now keep in mind they're oxidized because the sulfur here is bonded to a hydrogen, but it becomes bonded to another sulfur. If you remember that sulfur is in the same group of the periodic table as oxygen, this molecule has 1, 2, 3, and 4 bonds to elements in that group, while over here, if we were to ignore the right, because that doesn't really matter, we have 1, 2, 3, 4. This sulfur was in it, so it actually is bonded to another one, which is 5, so it's been oxidized. These disulfides are important in nature because they form disulfide bridges in proteins, and that actually helps to keep the structure of proteins together. And we can see here these little balls represent amino acids. So what we have here is the proenzyme known as preproinsulin, which that's an inactive enzyme essentially. But you'll see that in there we have the disulfide bridges here and here and here, keeping these parts of, I should say, the A chain and the B chain together. Eventually, when the pre-pro insulin gets to the places where it needs to work, it'll cleave off the gray balls, but you still have these disulfide bridges here keeping the A chain and the B chain together in the now active insulin protein or enzyme. The mechanism for this reaction, you can see the first step is deprotonation of the thiol from the hydroxide. This thiol has a pKa of 10.5, so it's less acidic than hydrosulfuric acid, but it's still more acidic than water, so this is definitely going to work. And then that results in the thiolate ion here and water. Remember, if we have an RO minus, this was an alkoxide. If it's an RS minus, it's a thiolate. And you should definitely never thiolate me. I don't want to be thiolated. The next step, oh, look, I just noticed an error in, I guess, transcription here or something. The negative charges have turned into alpha sign, or not alpha, the at signs. Oh my goodness. There's so much things getting messed up here. These should be those. There we go. And this is a sodium plus. The thiolate ion will attack the bromine, creating this thiobromide, I guess, intermediate in this reaction. And then another thiolate ion will attack the sulfur and kick off the bromine, creating the disulfide over here. The disulfides can be reduced using hydrochloric acid and zinc, and essentially that's just going to split that off and create the new thiols. So as it's seen, it's pretty easy to form sulfur-sulfur bonds. It's pretty easy to break them apart. And this is, again, important for the structural integrity of proteins. We need to be able to break them apart easily to cause certain enzymes to activate. We need them to be able to form, to get them into the right shapes and configurations. The bond dissociation energy is pretty small. It's not much different than a peroxide, right? A peroxide is this, and as I've mentioned, oxygen-oxygen single bonds are pretty weak, but so are sulfur-sulfur or disulfides bonds. The next type of sulfur-containing organic molecule would be the sulfides. Strangely, we started with disulfides and now we have the sulfides, but they just come next. This is how the book does it. Sulfides are also known as thioethers, and these are organic molecules that are similar to the ethers in that you have a sulfur between two alkyl groups. All right, now naming sulfides. They're named like ethers, but use sulfide instead of ether. So we have diethyl ether and diethyl sulfide. As substituents, they're named as alkyl thio. And so see below, what I mean by this, alkyl is just whatever the alkyl group is coming off. So in this left molecule, you have this one carbon chain coming off the oxygen, and we called the whole group, therefore, a methoxy group. For the sulfur, again, we have one carbon, so it's a methyl thio group, right? So it's a little different. We just call it methoxy or ethoxy. Here, we don't have that oxy part coming after, so it's easiest just to call it methyl thio. So the names of these molecules are 1,1-dichloro-4-methoxycyclohexane and 1,1-dichloro-4. Now it's methylthiocyclohexane. All right, so how to prepare sulfides, these ethers essentially, but with sulfur instead of oxygen. We're going to take sodium hydroxide and an alkyl halide. This is much the same as we saw for producing ethers earlier in this chapter. And what I mean by that was what we saw in the Williamson synthesis was what we would take an alcohol and deprotonate it. That used sodium hydride, not sodium hydroxide. The hydride would deprotonate the hydrogen, making this the alkoxide, I should say, and then that would attack some RX to create the ROR. In this synthesis here of the sulfide, you have the first step being a deprotonation of the thiol, and then you have the S- that would attack the R in an SN2 mechanism and create the sulfide there. So you can see the mechanism here, the first step being the deprotonation of the thiol from the hydroxide ion, creating water and the thiolate ion. The thiolate ion will attack the alpha carbon of the halide in an SN2 mechanism, creating the sulfide. Now we have some reactions that the sulfides can undergo. The first one here we have is attack of an alkyl halide via an SN2 mechanism. So the sulfide there will attack another alkyl halide in an SN2 mechanism, kicking off the halide and creating this ion right here. So it creates this intermediate ion, and then that intermediate ion can be further attacked by some nucleophile, and we can use these as alkylating agents, as it says there in 1.2. That methyl group that was added to the sulfur is now just getting removed from the sulfur, so you've reformed the sulfide, and now we've essentially made a carbon-carbon bond between that methyl group and some other carbon, whatever it would be. So it's a great way to build molecules. This isn't necessarily something we're using to create, or add to a substrate, but it can be used almost as an intermediary to build on other substrates by adding these methyl groups. It doesn't have to be only a methyl group, it can be any alkyl group as long as it's going to work with an SN2 mechanism. So here's an example. We have sulfur mustard, also known as mustard gas. It actually will react with itself, kicking off this chloride and creating this three-membered ring called an episulfide. So it's like an epoxide, but it's got a sulfur, so episulfide, and then, well, the sulfur also has this other carbon there, so it's positively charged. And then the nucleophile will attack right here and open it up, and now you've got this new group up here added. This slide shows how mustard gas can lead to cell death. It actually will alkylate two strands of DNA, cross-linking them together, because it'll kick off both of these chlorides as in the process, and this prevents the DNA from replicating properly, and if it can't replicate, eventually the cell just dies. In the 1930s, scientists or doctors were trying to see if they could kill cancer cells by alkylating the DNA in the cancer, and it turned out that it was just too toxic, so it didn't work. But in theory, cross-linking tumorous cancer cells, that are metastatic or whatever, would certainly be something we'd want to kill if it was able to be, directed only at the cancer cells, but didn't work for this case. Another biological use of this alkylating property of the sulfides is a methylation reaction between methionine, an amino acid, and ATP, or adenosine triphosphate, and that makes this SAM molecule here, or S-adenosyl methionine, which kicked off this inorganic phosphate group in the process. The SAM molecule possesses this methyl group, attached to that positively charged sulfur, so the SAM is a really good methylating agent. One use of SAM biologically is the production of adrenaline from noradrenaline, and in that the SAM is attacked at the methyl group right here by a nitrogen on the noradrenaline, kicking off the rest of that complex leaving group there, the SAM, and then it methylates the nitrogen, creating adrenaline. So the second type of reaction for sulfides will be that they can oxidize to sulfoxides and sulfones. You might think that it'd be more like making the carbonyl or carboxylic acid or something, but in fact the sulfur is almost like it's behaving like a carbon here. So we oxidize this sulfide, it makes the sulfoxide, which is again similar structurally to a ketone, and then that can further oxidize to a sulfone. In either case, the sulfur is neutral because you have either 4 bonds and 1 lone pair or 6 bonds. If you needed to stop at the sulfoxide, you'd use sodium periodate. And so for the example here, we have methylphenyl sulfide. Again, this would be a common name. You have a methyl group and a phenyl group, so you put those alphabetically, methylphenyl sulfide, and that will oxidize with the sodium periodate to methylphenyl sulfoxide. If you need to go further to the sulfone, you can use something like 2 equivalents of peroxide there, and that'll do it. And so methylphenyl sulfide can go to methylphenyl sulfone. All right, the true structure of sulfoxides and sulfones are kind of in question. We see the sulfoxide there could be with the double bond to the oxygen or a single bond. With the single bond, you get separation of charges. So this would be like an ylide, sort of. And you might think that this would be the preferred, but studies actually show that that resonance structure is significant. And with the sulfone, you get the same thing, but you have a 2+ charge on the sulfur rather than 1+ for the sulfoxide ion. And again, it turns out that this is a significant resonance contributor. In fact, I happen to know somebody who was a professor at Notre Dame who actually studied this himself and showed that the sulfur would rather be in the tetrahedral structure, the sp3 hybridization that we see over here, than having this set of 2 double bonds and hybridizing with d orbitals. So we will show it often like this because it gets rid of charges, it looks cleaner maybe, but in reality it may be both, but certainly the one that is charged for either of these, those are certainly relevant resonance contributors. All right, so the last thing here today will be the synthesis of this compound here. Let's name that. I would number it 1, 2, and 3. The highest priority functional group is the alcohol, which means that that's the longest continuous chain of carbons that contains the alcohol. So this is actually 1-phenyl, 2-propanol. All right, and we're trying to get that from bromobenzene over here. There's certainly multiple ways you could do this. We have a bromine there on a benzene ring, and you might look at that and be like, well, what can we do? We've seen bromines actually do stuff, and if you look at the product, we have this benzene ring here. And then we've got the other group that I'm going to box in red. All right. Well, what we can do, simply put, is just take some compound of 3 carbons with an oxygen. All right. Maybe you want to use a ketone like this, and then use a Grignard reagent to do that reaction. So you convert this to some MgBr, which really just makes that carbon negatively charged and could attack, but it's not going to attack at the right spot. So that's really not going to work. So instead of using some sort of carbonyl, maybe instead you use an epoxide. I know this is going back, but this is synthesis strategies involving epoxides, so that should be pretty obvious what we should do here ultimately. But again, we have this epoxide, we have the bromobenzene, we'll convert it to methyl, or this phenyl magnesium bromide, and then that could attack, hitting the epoxide there, opening up the ring like that, and then you would protonate in the final step and you get your 1-phenyl 2-propanol product. So that one, just don't forget about the epoxides. They're very useful. Carbonyls certainly are good. Leaving groups may be good. But also keep in mind, you couldn't, I should have mentioned, you couldn't use something like this directly. Again, if we have the magnesium bromide there and this becomes negative, you might look and say, well, that'll just kick off this iodide, which will be a better leaving group than a bromine that's also present there, and then you're done. Well, the problem is you've got this hydrogen there, and this is a Grignard reaction in a sense, using the Grignard reagent, and those are going to protonate first. The acid-base reaction will come first over the SN2. And so that's not viable. So if you wanted to do that and you had an iodide here, you would need to convert the alcohol into a protected group, such as the trimethylsilyl group. So OTMS here would be a good, and then that would work. But you've got to have this one, which is also weird in the first place because it's got an iodine. Then you've got to protect it. Then you've got to make the Grignard reagent. Then you've got to do the reaction itself. So that's a lot of steps right there. So the easiest is just to use that simple epoxide, which sure, you may need to make the epoxide and then the Grignard reagent, but I guess maybe there's multiple options here. So the first one I would say is using magnesium in diethyl ether. The second stage would be to react it with the epoxide, and then the third step would be some H3O plus to get that final protonated alcohol there.